Okay, a couple weeks ago you had the assignment of going to this site and looking at distributions a bit. Um, I wanted to go through it because I think there were some points that didn't come clearly through based on the responses. So the first thing you were supposed to do is click on the sampling options, and that gives you three distributions, or you can at least see where they're going to be here. These are very different types of distribution, and that was one of the points that I was trying to make with this site. I think it's one of the reasons this site was created. So this is the excuse me, this is the original population data over here, and so these bars represent, the higher bars represent the greater number of students that are getting that hour of sleep. So if we look at, for example, just this one bar right here, what does that mean? Well, that means that if we go over to the y-axis, maybe 800 students had between maybe 5 minutes 45 and 6 hours of sleep out of what total number of students? Well, I go up here, population size 18,000. So I have 18,000 students that are getting between 5.75 and 6 hours of sleep per night. And then if I go to a different bar, say this very top one, there's going to be over 2,000 students there that are getting right at about 8 hours of sleep. If I were to add up all of these bars and how many students they represented, I should get 18,000 because that's my population size. And in fact, I could scroll down and see these all one by one, the data there. And again, fake data. I mean, what college student gets 8 hours of sleep, right? Okay, so we have three graphs, and let's see, what was your next step? Oh, looking at the mean and standard deviation of each one are always reported. So we do see that average is about 8 hours of sleep, standard deviation 1.5. So real quick, one of the things we can think of interpreting that, because it is about normal here, 1.5 above and 1.5 below should give us 2/3 of the data, the majority of the data. So that's between 6.5 hours and 9.5 hours. So that looks about reasonable in the graph there. Now we're going to change the sample size to 7 right here and draw samples. Okay, so drawn the 7 students in our stats class. We do have quite a few more there, but I did want you to be able to see the individual dots. So what's the difference between this and this? Well, this is just 7 out of the 18,000 students. Every dot here is a single student. And the cool thing is you can see exactly where these dots came from in the population. Notice that we're more likely to get students in the center range because there's so many students to draw from. In fact, we got 2 from that big bar right there, where we didn't get any from these 5 or 6 bars out on the end because they are smaller, so we're less likely to get them. So not only did we choose these 7 points, but they calculated the mean for us. And so what we're going to see over here in this third graph is that single mean. So this dot right here represents the mean of these 7 students chosen from the population. So population, sample, sample, mean. Okay, and oh, one thing here, notice that the mean here is 7.6, which is not too far from 8, but it's certainly not right on there. Okay, now we're going to change the number of samples to 10 and click on Draw Samples. So what we have here is the most recent sample. This is still just a single sample of 7 students, and again, we can see where they came from. We did get one out here towards the edges, but still mostly in the middle. Notice this sample mean was a bit lower than the other one we had. So here we can see all these plots growing on this one. Each of these dots is a single sample of 7 students that was taken, and then the mean was calculated. So we can see the highlighted blue one is the most recent sample, but each of these was 7 students randomly chosen from this population. The mean was calculated, and it was plotted right here. Okay, now we're going to change the number of samples to 10,000. Make sure I did that right. 10,000. And this may take just a second. Okay, now what do we have? Well, we notice that this graph now looks a lot like this. Why? What does this mean? Well, it turns out that that's more or less just coincidence. Because this happened to be a normal, this one will always be a normal. So the distribution of sample means will always have a normal shape no matter what this shape is. So the only reason they matched is just because this one happened to be normal. But no matter what this original population, the entire population shape looks like, this sampling mean distribution will be normal. And keep in mind, each one of these points is not a single student. Each one of the blocks that make up this count, so here if we go over here we have maybe 1,700. That's not 1,700 students. That's 1,700 sample means, where each sample size was 7, calculated the mean, plotted it over here. Notice that the standard deviation is 1.5, and here it's 0.575, so it's much smaller. Why is that? The sampling mean has a different standard deviation than the original population. It's connected, but this is called the standard error. So the standard deviation of this distribution right here is called the standard error, and we calculate it by the original standard deviation divided by square root of the sample size. So if we took 1.51 divided it by square root of 7, we should get about this. However, the mean of the original population and the mean of the sampling distribution are going to be almost equal. And the more samples we take, the closer that those are going to get percentage-wise. Okay. Let's see. Okay, so population 3 now. So notice this is very much not a normal distribution, not a bell-shaped curve. And we're going to change the sample size to 100. Okay. So we're trying to figure out what the graph at right will be. Well, the central limit theorem tells us 3 things about what this graph is going to look like. It tells us that no matter what, it will be bell-shaped. So we don't care about this population. This is going to be bell-shaped. The mean of this population should be about the mean of the original population, so about 8 again. The standard deviation of this population should be the standard deviation of the original divided by square root of sample size. I intentionally chose this, so square root of 100 is 10. So we can divide this by 10. So we should get about 0.47 for a standard deviation. And again, we may be a little bit off because there is this concept of randomness, but those are the limits that we're approaching. So the central limit theorem would tell us that with 10,000 samples, we should be getting pretty close to those expected. So let's see. Takes just a while. That's a lot of samples here. Now we have sample size 100. So we do indeed have the bell-shaped curve. In fact, we can put this normal distribution over that to see that it's very nice bell-shaped curve. The mean is 8. Standard deviation is 0.47, exactly what we were hoping for here. And notice over here, another thing, when we're having sample sizes of 100, what's happening here? This is going to look very similar to our population because the greater a bar is over here, the more likely we are to get a single dot over here, and the smaller it is, the less likely. So we're going to imitate the shape. But the difference between this graph and this graph, or really these two graphs, is that we're taking the mean of the sample to plot this. So this is not original data like this and this are. The counts up here represent sample means, and there are some very special things about the means, namely that bell-shaped curve. We know that the mean of this distribution is going to roughly equal the mean of the population, and we know the standard deviation will be this standard deviation divided by square root of n. So when we're dealing with inferential statistics, keep in mind that this is the distribution we're working with. This is the more complicated one to understand. These two are both fairly easy to understand. This is what is out there that we're really interested in. This is what we get to see when we actually collect the data. But this is the engine. This is the motor driving everything, all of the inferential statistic tests, is this sample distribution of the mean, or sampling of the mean distribution. Okay. So I think that hopefully clears up some things about what this is and why it's important, but please feel free to ask more questions.